The famous scientist Michael Faraday discovered a link between electricity and magnetism that we now call Faraday induction. And that's what we're going to demonstrate today with this simple apparatus. We've got a large coil here, and it's connected with a wire to this sensitive meter, this voltmeter, and we've got magnets. Now the voltage that's generated by a coil of wire is dependent on the number of turns of wire, the area of the coil, and the strength of the magnetism, and also the rate at which you can change the magnetic field. If the magnetic field is fixed and you can't change it, then the equivalent is actually moving the coil, so you can move the coil. Now in the UK, the Earth's magnetic field is about 50 millionths of a Tesla. So what voltage would we get in our coil if we could use the Earth's magnetic field to generate electricity? And if you put the numbers in the formula, we've got 1,000 turns of wire, we've got about an area of 1/4 of a metre squared, we've got the Earth's magnetic field, which is 50 millionths of a Tesla. If we can pick up the coil and move it once a second, 1,000 times 1/4 times by 50 millionths times by 1 gives us a voltage of about 100th of a volt, or 10 millivolts. So let me demonstrate that to you. I'm going to pick up the coil, I'm just going to move it. So now as we move it, the Earth's magnetic field is inducing electricity into the coil. And you can see on the meter we get a very small reading, but it's about 10 millivolts, which is what we expected from our little formula. So what would we get if we could use a much more powerful magnet? This is a rare earth magnet, and the strength of the magnetism on the top of the magnet is about 10,000 times that of the Earth's magnetic field. So you'd think that if you put this in the coil, you get 10,000 times more electricity. The problem is, because it's such a small magnet, the magnetism drops off quite quickly. So by the time you get to the size of the coil, it's also quite a feeble magnetic field. So you don't get as much as you think. What I've done here is I've fixed a number of these magnets onto the paddle. And of course it's going to give us much more magnetism. And as I move this in and out of the coil, you can see that it generates electricity beautifully. So this is demonstrating Faraday's induction. Now the first thing you see is as you bring the magnets in, because you're increasing the magnetic field, you get a nice positive signal. If I leave the strong magnets right in the centre and don't move them, the signal goes to 0. So you only get electricity if you actually move the magnets. If the magnets remain still, you don't generate any electricity. Now if I take these magnets out, I'm going from a large magnetic field to less magnetic field. You get another pulse, but it's negative. So basically, you can constantly generate voltage in the coil only if you constantly move the magnets. It's alternating voltage. As you move the magnets in and out of the coil of wire, you're inducing electricity into the coil. You get a plus signal, a naught, a minus signal, a plus signal, a naught, a minus signal. You're getting this, what's called an alternating current or voltage. So basically what you're doing is you're converting mechanical energy by moving the magnets into electrical energy. And that's really how modern day electrical generators work, on this same principle.